Now, kind of zooming up a little bit, we talked about the problem way back at the beginning. This thing called Q-Day is coming. RSA and Diffie-Hellman and the other public key cryptography methods that rely on the integer factorization problem, they're now susceptible to quantum computer attack, and in the future, or even now maybe. And there's this harvest now, decrypt later technique, which is happening right now. So what are some advancements you can make to protect yourself and become quantum safe going forward? So we show three of them down here. The one I'll talk about first is in the middle, and you may have heard of this quantum key distribution, which is abbreviated QKD. This has been around for more than a decade. It has never caught on because it's got some limitations that are pretty serious. It does involve using single photons and encoding them, but instead of generating entanglement between Alice and Bob, instead Alice encodes a photon and sends it down the fiber for Bob to receive. So it's different, and in order to, because you're dealing with single photons, you're going to have a distance limitation. There's only so long a single photon can travel down a fiber without, being lost. So what you have to do in QKD, which uses a protocol typically called BB84, is you have to have a trusted relay point or many along the way between Alice and Bob, where you decode the secret, decode the quantum state that's on the photon. It's in clear view at that point. Then you re-encode it and send it along the next hop. So that relay node has to be trusted by the two parties. And generally, the principle that's very important in security these days is zero trust. You shouldn't have to trust the relays along the way. So that's QKD. On the left is PQC. This is the idea of moving to new math algorithms that are more resistant, especially to quantum computers and Shor's and Grover's algorithms, than RSA and Diffie-Hellman and the others we use today. So there's a lot of work that's gone on in terms of candidates for this PQC, and there's some final algorithms that in the US, the NIST has put out. Some of the algorithms, many of them were broken along the way. You don't know when these algorithms are going to be broken. And you're still exposing your keys in the public with a new kind of a math encryption. So that's why over on the right, we say that using entanglement is the ultimate in security. We call, to distinguish it from what's in the middle here, we call it QSC, quantum secure communication. So now you're using single photons, but you're not sending them one at a time from Alice to Bob. Instead, Alice and Bob exchange, they are sent one pair of entangled photons, and they measure them. So the only parties that know what the state of those photons was are the two parties that measure them, and if they were entangled, they know they were identical. And that's how QSC works. So it's the most secure. It's also, if you have a good, capable software stack that can work with different types of hardware, then it's also a future-proof approach.